In this video, we're going to discuss the concept of stoichiometry. Stoichiometry is defined as the calculation of the relative quantities of reactants and products in a chemical reaction. So it's a very important type of calculation where we're able to calculate the mass or the amount of reactants and products in a chemical reaction. Stoichiometry is founded in the law of conservation of mass, which of course states that in a chemical reaction, mass can neither be created nor destroyed. So this allows us to know that the total mass of the reactants that are used in a chemical reaction must equal the total mass of all the products that are produced, since mass can neither be created nor destroyed. So stoichiometric calculations enable us to answer certain very fundamental questions that we often need to know as chemists. For example, in a chemical reaction, what mass of a product may be produced from a certain mass of reactants? That can be very important if you're performing a chemical reaction. Secondly, what mass of a reactant or reactants are required to produce a certain mass of a product? Also, what mass of one reactant is required to completely react with a given mass of the other? So these are just a few examples of some fundamental questions that we'll be able to answer when we become familiar with stoichiometric calculations. So at the heart of a stoichiometric calculation is the molar relationship given by a balanced chemical equation. Let's take a look at the reaction between sodium solid plus chlorine gas to give us sodium chloride. Now, this isn't balanced. If we balance this, of course, it would look like this. It's important to appreciate what these coefficients tell us. For example, this chemical equation can be read as 2 sodium atoms will react with 1 chlorine molecule to produce 2 sodium chloride compounds or formula units. You could also read this as 2 moles of sodium atoms will react with 1 mole of chlorine molecules to produce 2 moles of sodium chloride. So we can appreciate these coefficients to represent either molecules or atoms or moles of molecules and atoms. However, these coefficients do not represent masses. We couldn't say 2 grams of sodium will react with 1 gram of chlorine to give us 2 grams of sodium chloride. That would violate the law of conservation of mass. If we have 2 grams plus 1 gram, that doesn't equal 2 grams. That matter would be destroyed in that case. So be sure that you have a good, solid understanding of what these coefficients tell us in a chemical reaction. So in order to calculate the mass of products produced or the mass of reactants used in a given chemical reaction, we must use these ratios here that we talked about before. 2 moles of sodium reacting with chlorine can produce 2 moles of sodium chloride, or 1 mole of chlorine gas will completely react with 2 moles of sodium atoms. So these are the important stoichiometric relationships that we want to appreciate. Let me give you an example that illustrates this, a little simple example. Let's say we want to produce complete cars. 1 car body plus 4 tires will give us 1 complete car. So these coefficients represent our or are analogous to our stoichiometric coefficients in a chemical reaction. So look at this question. If you have 8 car bodies, how many tires are required to react, or how many tires are required to add to 8 car bodies? Well, to do that, we need to look at our stoichiometric relationship. One car body requires 4 tires. So if we have 8 car bodies, well, of course, we would need 32 tires to completely react with or completely add to our 8 car bodies. Now, if we have 8 car bodies and at least 32 tires, how many complete cars could we produce? Well, again, our relationship tells us that for every 1 car body, if we have enough tires, we can produce 1 car. So we would be able to produce 8 complete cars. So these represent the relative amounts that these are quantities that these things combine in. 1 car body plus 4 tires reacts with 1 car, or reacts to form, or combines to form 1 car. These coefficients, again, do not represent masses. We could not say 1 kilogram of car bodies plus 4 kilograms of tires will produce 1 kilogram of cars. Again, these ratios here represent amounts of things, not masses. So let's practice a couple of problems that involve stoichiometric calculations. Let's take a look at this problem here. Iron reacts with molecular oxygen to form iron 3 oxide, also called rust. How many grams of iron 3 oxide can be formed from 5.47 grams of iron and excess molecular oxygen? And part B, what mass of molecular oxygen is required to completely react with the 5.47 grams of iron? So let's go through this problem step by step and see how we would solve it. The first thing we would need is, of course, a balanced chemical equation. So the chemical equation, iron, Fe, solid, reacts with molecular oxygen. Molecular oxygen is O2 gas, and that forms iron 3 oxide, Fe2O3, which is a solid. Now this chemical equation is not balanced. We have 1 mole of iron over here and 2 moles of iron on the product side, so we know it's not balanced. So we can balance this equation, and now we have a balanced chemical equation, which gives us the ratio of the amounts of these compounds and atoms that they'll react. So the next thing we need to do is, once we have our balanced chemical equation, let's determine a strategy for solving part A. We want to know how many grams of iron oxide, what's the most grams of iron oxide that we can produce from 5.47 grams of iron. And we're told that we have as much oxygen as we need. There's only one relationship that we know between the iron and the iron 3 oxide. The only relationship is given by our stoichiometric coefficients. For every 4 moles of iron that we react with our oxygen, for every 4 moles of iron, we can produce a maximum of 2 moles of iron 3 oxide. So we need to use that relationship, that molar relationship, as the heart of our stoichiometric calculation. So I know the ratio that 4 moles of iron will react to form 2 moles of iron oxide, iron 3 oxide. However, I'm not given moles of iron, I'm given grams of iron. And I'm not asked for moles of iron oxide, I'm asked for grams of oxide. So I can build on this relationship because I can convert grams of iron into moles of iron. I can convert grams of iron into moles of iron using the molar mass of iron. Once I have moles of iron, I can use that relationship, that ratio given by my balanced chemical equation, to convert moles of iron into moles of iron oxide, iron 3 oxide produced. Then, once I have the moles of iron 3 oxide, I can convert that to grams using the molar mass of iron 3 oxide. So this is the strategy I want to do. I want to convert from grams of iron to moles of iron to moles of iron 3 oxide, and then moles of iron 3 oxide to grams of iron 3 oxide. But I want to reiterate any type of stoichiometric calculations involving chemical reactions. You're always going to need to use that ratio given by your balanced chemical equation, the stoichiometric relationship given by those coefficients. So let's set this up. Let's start with our grams of iron, and let's convert that to moles of iron using the molar mass. Again, I have grams of iron, so I want grams on the iron on the bottom and moles of iron on the top. Now I can use my ratio for my balanced chemical equation. Remember, 4 moles of iron will react to form 2 moles of iron 3 oxide. So I got the 2 and the 4 from the balanced chemical equation. Now I can use the molar mass of iron 3 oxide. 1 mole of iron 3 oxide. I want moles of iron 3 oxide on the bottom, and I want to end up with grams of iron 3 oxide. The molar mass of iron 3 oxide is shown here. Now I can solve this, and I get 7.82 grams of iron 3 oxide can be produced. So that's the maximum mass of iron 3 oxide that can be produced from 5.47 grams of iron. This number is also what's called the theoretical yield. The theoretical yield is the maximum mass of a given product that can be produced from a certain mass of a reactant. So you'll hear that term. You want to be sure to be familiar with the theoretical yield, and that's what we've calculated here. So this 7.82 grams of iron 3 oxide is the maximum mass that can be produced from our starting mass of iron, 5.47. So let's take a look at part B. Part B says what mass of molecular oxygen is required to completely react with the 5.47 grams of iron. So we're given 5.47 grams of iron. We have a lot of oxygen, but how much oxygen is actually used in the reaction? Well, to solve this, again, we need to be sure to use our ratio of our coefficients, so our stoichiometric coefficients or stoichiometric ratio. This tells me that for every 4 moles of iron that I react, I will require 3 moles of oxygen to react with that. So this is a 4:3 ratio. So I can use that ratio to convert from moles of iron to moles of oxygen. Again, that's going to be at the heart. However, I need to first find the moles of iron. So I can convert my grams of iron into moles of iron using the molar mass of iron. Then I can use my coefficients, my ratio from my balanced chemical equation to convert from moles of iron to moles of oxygen. Then, when I have moles of oxygen, I can convert that to grams of oxygen using the molar mass of oxygen. So it's a similar strategy that we used before, and you'll see that most stoichiometric calculations follow a similar path. So let's start by converting our grams of iron into moles of iron. And I want my grams of iron on the bottom here, so the grams, units of grams will cancel and end up with moles of iron. Next, I'm going to use my stoichiometric ratio. 4 moles of iron can react with 3 moles of oxygen. So the 3 and the 4, those come from the balanced chemical equation. Now that I have moles of oxygen, I can convert it to grams of oxygen using the molar mass of oxygen. Again, I want moles on the bottom, grams on the top. Solving this tells me that 5.47 grams of iron will completely react or require at least 2.35 grams of oxygen to react with it. So now this is not a theoretical yield because it's a reactant. Theoretical yield must be a product, but this is the mass of oxygen that is required to completely react with 5.47 grams of iron. One other thing you want to notice, we mentioned earlier that stoichiometric calculations are rooted in the law of conservation of matter. We said that 5.47 grams of iron will completely react. We calculated 2.35 grams of oxygen and will produce 7.82 grams of iron 3 oxide. If we add the mass of our reactants together, that gives us 7.82 grams, which is the mass of the product that was produced. So the mass of the sum of the masses of my reactants is equal to the total mass of products produced. Again, this demonstrates that we did indeed follow the law of conservation of matter. So in general, when you're asked to perform some stoichiometric calculation, in other words, where you're asked to convert from one substance, the mass of one substance, to the mass of another substance, whether it's one reactant, figure out how much of the other reactant is used, or given a mass of one reactant, how much of another product can be produced. You will always use this molar ratio, the ratio of coefficients between the two things that you're looking for. So here, if we want to convert from A to B, we would start with grams of A. If we were given the mass of A, we would start with the grams of A, and we would convert that to moles. Then we must use that molar ratio to get from moles of A to moles of B. And then once we have moles of B, if we're asked to get to grams of B, we would use the molar mass. Okay? But regardless, you'll always use this molar ratio given by your balanced chemical equation. That's the heart of every stoichiometric calculation. So let's look at one more problem dealing with stoichiometry. In this problem, you're told that nitrogen gas reacts with hydrogen gas to form gaseous ammonia. What mass of nitrogen and hydrogen are required to produce 50 grams of ammonia? Okay. So you're asked to do two separate problems here. First thing is you're asked to calculate what mass of nitrogen, you're given the balanced chemical equation here. You're asked what mass of nitrogen is required to produce 50 grams of ammonia. And then secondly, you'll do a second problem where you'll calculate what mass of hydrogen gas is required to produce 50 grams of ammonia. So do those as two separate problems, part A and B. Again, even though you're starting with the product and you're asked to figure out how much of a reactant is required, you'll follow that same pattern that we discussed before. So what I'd like for you to do is pause the video, do your best to solve these problems, and then replay the video and take a look at the solutions. So go ahead and pause the video. Okay. So let's see how you did. Let's solve part A first. What mass of nitrogen is required to produce 50 grams of ammonia? Well, I need to look at the stoichiometric relationship between ammonia and nitrogen. 2 moles of ammonia can be produced from 1 mole of nitrogen given excess hydrogen. So we can use that stoichiometric relationship to convert from moles of ammonia to moles of nitrogen. So I'm given the mass of nitrogen, I'm given the mass of ammonia in grams, so I can use the molar mass of ammonia to figure out the moles of ammonia. Then I can use my stoichiometric ratio between ammonia and nitrogen. That's going to allow me to figure out how many moles of nitrogen are required. I can then convert the moles of nitrogen required to grams of nitrogen required using the molar mass of nitrogen. So let's go through those calculations. We're going to start with ammonia, 50 grams of ammonia. I'm going to convert that to moles using the molar mass of ammonia. 2 moles of ammonia require 1 mole of nitrogen. And then I can convert from, and I get this, of course, from the balanced chemical equation. That's my stoichiometric ratio of the coefficients. Then I can convert moles of nitrogen required to grams of nitrogen using the molar mass of nitrogen. Here we have 41.12 grams of nitrogen required. As always, be sure your answers are expressed to the correct number of significant figures and you have units. 41.12 grams of nitrogen are required to produce 50 grams of ammonia. Let's look at part B. Again, we want to use a very similar strategy. I'm going to look at the ratio of coefficients. 2 moles of ammonia require 3 moles of hydrogen. So I'm going to use that ratio the ratio of the coefficients from the balanced chemical equation. That's going to convert from moles of ammonia to moles of hydrogen. However, I need to get first from grams of ammonia to moles of ammonia. So I'm given 50 grams. I can use the molar mass of ammonia to get to moles of ammonia. Then I can use my balanced chemical equation ratio. That will tell me how many moles of hydrogen are required. And then to get to grams of hydrogen required, I use the molar mass of hydrogen, H2. So you can see the calculations here, 50 grams of ammonia. I use the molar mass of ammonia to calculate the moles of ammonia. This is the stoichiometric ratio of the coefficients from my balanced chemical equation. I want moles of ammonia on the bottom, moles of hydrogen on the top. Then I can use the molar mass of hydrogen to convert from moles of hydrogen to grams. Again, to the correct number of sig figs and units, we have 8.878 grams of hydrogen are required to produce 50 grams of ammonia. So that's the minimum mass of hydrogen that you would need to produce 50 grams of ammonia. And we can also check our work here to be sure that we did obey the law of conservation of matter. We calculated 8.878 grams of hydrogen are required. 41.12 grams of the other reactant, nitrogen, are required to produce 50 grams of ammonia. So if we add up the total masses of our reactants used, that equals 50 grams, which is the mass of the product produced. So no matter was created nor destroyed. So be sure you practice some more of these stoichiometric problems. They're very important. We use them all the time in chemistry. And be sure you understand the strategy that we discussed. So good luck.